Okay, here we're going to pick up where we left off. We just created the mesh scene. So we'll pull that up again. We'll create a new one. And wait for a minute for it to come up. There it is. So, as we said before, it'll be adequate for a quick simulation on this laptop. So now we're going to go into and we're going to talk about the continua. So when we created the automatic mesher here, it automatically created a physics continua, and we need to go in and define our models. Let's go ahead and do that. Select models, and for this specific case, we're going to do a steady. Even though there's rotation, it's going to be imposed in a reference frame rotation. And so that means it's only solving for a single instance in time instead of as the propeller is actually moving. So it's just going to impose a rotation. So we'll say steady. We're using a gas. We're going to use a coupled flow for this case, and then we're going to do an ideal gas. And then for this case, you can do it turbulent. But for this case, we are going to speed up the process and do it inviscid. So those are the physics continua for this case. Okay, now that the physics continua has been defined, we are going to go in and work on the interfaces and also the boundary conditions. So we'll open up the boundaries on everything. So here we have the free stream, the in, the different ins, the different outs. And so for this simulation, we're just going to make things simple. If you wanted to do it a more comprehensive simulation, we would have chosen a turbulent regime, and we would specify the Mach number on the inlet. And but for this, for simplicity's case, I'm going to choose free and inlet, and the other free and the other inlet. And so all of these we want to edit and say that these are velocity inlets. And we're going to go ahead and make sure that the direction is in the correct boundary normal. We don't want to do that. We want to do components because we're doing the sides. And so flow direction, constant laboratory, good. We want it in the x direction. As you can see, x is our direction of the fluid motion. And our static temperature should be constant. 300 K about room temperature is good. If you want to try and do a validation study, you'll need to change that. And the velocity magnitude, for our case, we're going to do 10 meters per second. And so that should do it for the inlet. And the outlets are something similar, but we are going to do a pressure outlet. Okay, and so just going back into that, on the pressure outlet, we want to have it as 0, and the static temperature should be the same as the inlet, unless of course you're doing a validation study and that's not the case. But here, this is a reference. It's referring 0 relative to another pressure, which the master pressure is set in the continua in the physics models, and so it's in the reference values. And so here, this reference pressure, we'll want to change that to in this case it's 1 atmosphere, which is good for this study. So now that we have the inlet and the outlet set, now we want to start setting up our interfaces. And so we've got this symmetry 1 and this symmetry 2. And so we'll want to create an interface for this, like so. And then we'll need to do it for the internal as well. And so we can make this transparent so we can kind of see a little bit better. Again, that was that button right there. So we've created the interface on the outer surface, this upper and lower. Now we want to create the interface on the upper and lower of the rotating puck. And so we'll find that is rotation symmetry 1 and rotation symmetry 2. And we'll create this other interface. And then we need to start matching these internal interfaces. And so let's start at the rotational back. So it's the top and it's the back. And is it this one? No. Here it is. So we want to choose these two. They're the same. Create an interface there. Here at the top of the curved surface. And that as well. Create an interface there. Front and the front. Create the interface. Bottom, back, and the bottom back. The bottom of the rotational, the curved, and then the bottom of the front. Okay, now we have all of the interfaces should be set up. There should be 1, 2, 3, 4, 5, 6, 7, 8 interfaces. Let's go check to make sure that that is the case. It seems to be the case. So now what we can do is this interface as well as these two have the same type of conditions, and they're actually a periodic. And so, which means that the conditions that are on this part will be translated and imposed onto this part. And so the boundary, and so it makes a periodic about the axis. If you were to create a symmetry plane, it wouldn't do the same thing. It'd be as if the propeller was rotating this way and from the other side this way. That's not the case. We want the entire propeller to be as if it's rotating in one direction, both sides. And so periodic internal interface is good. The default conditions should be good for that. Okay, now for the rest of the interfaces, they are all the same thing, but they're different. They're not a periodic, but they are actually a mixing interface, and so that way it takes the information that is on this side and it mixes it, averages it over the plane, and goes into the other side. And so the reason for that is that the reason that these boundaries are so far away from the propeller is so that it has time, and so any error from the mixing can be negated or minimized. So there we have our all of our boundary conditions and the interfaces. Okay, so now that we have all of the boundaries and the interfaces set, let's go ahead and save the model, but this time let's go and save as, and so we kind of have a checkpoint. So here we have, example 2.0. Sometimes I like to do this so that if you make a mistake, you have a checkpoint to go back to. So we'll go ahead and save that. We can close these. And now we want to impose the rotation. That this model is a steady, and it's a steady state conditions, but we're imposing a rotation on this, on the central rotating region. And we do that by opening up the tools and going into reference frames, and we want to create a new rotating reference frame, but not translating, and we want to go ahead and edit that. For this case, the axis direction, the default setting is in the Z direction. That's not the case for ours. It's in the positive X, and so 1, 0, 0, we'll find that correctly. Axis origin is good, and the rotation rate, in our case, we're going to do negative 8,000 RPM. So we actually have a validation study that is similar to this, and we're developing the model for this. So now that that is set, we want to go and apply this reference frame to the rotational region. And so we do that by opening up the node and the physics values and the motion specification. So we want to edit that, and we want to say that it's actually rotating, and it makes the other node disappear, which is fine. So now that this is rotating, and the fluid region is not rotating, as you can see, laboratory stationary frame. Now we have our relative reference frame is set up. Okay, now with the relative reference frame updated and applied, we are going to make sure that the directions of the axes are in the same for both regions. If they're not, these interfaces will not work. So we're going to go ahead and edit this and go in here to the physics values axis, and the direction is in Z, so we need to change that to the X. And again, this has no motion specification, and let's make sure that the motion specification on this is set correctly as rotating, and then it should be the same. So let's just go ahead, and I've already got the residuals up here. When you press the run button, the residuals will come up automatically, so we'll see what happens when we run. So we'll just see if it will start to converge. It's starting to go down, so it'll probably be good. As a side note, I changed one thing in the physics, which was here in the initial conditions. In the velocity, I changed the velocity to the same in the x direction as all of the inlets. So we'll let it keep running here for a while, and we'll see if it converges. If not, we'll have to change a few things. Okay, so it seems like our solution is starting to diverge a little bit here, so we can go ahead and change a couple of things. First off, let's take a look at the mesh scene. We'll go ahead and make a new mesh, and we want to take a look at the inside. So we'll go and make a new derived part. We want to do a section and plane section. We want this with the normal to the y direction. And so now it's in the center, so we'll create that and then close. We have our new derived part, so we'll go into the scene properties, and we'll go into the mesh and the parts. Let's see if it'll open. And so now we want to look at just the plane section. That will give us inside and inside. Looks like we have prism layers on some of these edges, so let's go ahead and take those out. So we can do that by, in our geometry, in our operations and automated mesh, we can go ahead and look at these custom controls, and in everywhere except the prop, we can tell it to not have the prism layers. So disable, we'll do that for all of the rest. Okay, so now that all of those are done, let's use those extra cells that we have and bump down the mesh size just a little bit to see if we can't get it to converge a little bit better. So here's our base size. We'll say this is 0.08. And we'll try that and redo the array mesh. This should automatically do the surface wrapper as well. Okay, now that this is finished, the mesh, we'll take a look at it. Looks like the prism layers are now gone. They're only around the propeller. If you wanted to better refine the prism layers around the propeller, you would do that by going into the automated mesher, and in the meshers and double clicking here on the prism layer, and you can adjust any of these settings, and it's kind of an art. But for our study, we are going to bypass that and go right ahead. So let's go ahead and make a new scalar scene, and we can do that either there or here. And in this new scene, let's feed in the plane section. And then for our scalar field, let's do a velocity magnitude. So we don't want to do the rotating, but the lab reference frame. And let's go ahead and say that the maximum value is 50 meters per second. We can initialize that. Everything's initialized. Let's start running again. We'll see what happens. So, watch the residuals. It's hard to tell after just a few iterations, but hopefully they will go down this time and not come back up. And our STAR-CCM will come in. We'll see that we're starting to develop some of the desired solution of an increased velocity in the wake of the propeller. So looking at the residuals, it does look like it will converge in this case, which is very good. So we got rid of some of the numerical error, and so this is excellent. So it looks like it's going to work. Okay, now that we have an idea that it's actually going to work, let's go ahead and save it. And let's go in and make some reports and monitors. So the first thing we want to do, I've already made it, is a force, but we want to say new report and force. That creates this force monitor here. And we want to input our part as the propeller surface. And reference pressure, this is good. Pressure plus shear in the x direction. So this will give us our thrust. So this looks good. And the next report that we want to do is a moment. And this, we also want to do just the propeller surface. And these reports, they only report the forces on half of the propeller, as we've only modeled half of the propeller. So this axis of rotation is in the x. Should be good. So this will be the torque, and from the torque times for the rotational velocity is the power in, and the power out is the thrust times by the wind tunnel speed. In this case we have it as 10 meters per second. So now we have those two reports. Create a monitor from the report, and this will be good when we send it off to the supercomputer so that we can tell how it's converging or not, and if it is converged, and how many iterations it needs to converge. So we'll run it for just a little bit more, and we'll kind of see what it's doing. So torque, let's look here at the thrust. So for this particular propeller with the size and the rotation speed, the wind tunnel testing we've done shows that the accurate solution is about 0.3 newtons, negative 0.3 in this case, for the entire propeller, and half of that for just one side. And so your physics conditions, including turbulence and the different models that you use, will affect that, as well as whether or not you include compressibility in the Mach number. And the other thing that will affect that is the mesh. So looking at this, the residuals are continuing to go down. The range of this is relatively small, but it should come and converge somewhere close to the correct value for the propeller for the studies that we've done, the physical studies in the wind tunnel. But as you can see, it's looking great. And so what we want to do is we want to make our lives a little bit easier. We want to bump up our computational power by using a supercomputer, as well as tell STAR-CCM to basically run itself and do an iteration. And we can do in this example, we'll do a sort of a grid convergence study. And so some of the things we want to do is we want to make a Java macro, and we can do this by pressing this record button here, and we'll call this macro, and save that so it's in there in the STAR-CCM in the folder we've been working in. And then now that it's recording, anything that we do, that any significant action, it will record it in this macro. And so one of the first things we want to do is we want to change the base size. So operations and our automated mesh, default controls, and the base size. So we'll just do the things that we'd want it to do, and then it will record the we'll record it, and then we can go ahead and put in different values for it. So we'll change the base size to say maybe 0.2, something really coarse, so that we can run it really quick. Once the base size is changed, we want to run this mesh, and this should run fairly quickly. And then after this is finished, we will want to have it save. And so every iteration, every different mesh size, we want it to save out a new file. And so once this is done, we will tell it to save as. And this should just take a few more seconds. Okay, now that the automated mesh is finished, we want to save as, and we'll say there's a new file name. And now, once we have that, we want to tell it the execution to run. But before we run, we want to tell it to change the stopping criteria, especially the maximum steps, or else it will get to 1,000 and it won't go anymore. So we can change that to let's just change it to, what are we at, 36. So let's go 38, and when we adjust the Java macro, we'll change this. And so once that is finished, we'll tell it to run, and then so it's run just a few, and then it's stopped, and after that we want to tell it to save again, save. And so if we look over in our macro, it should have just about everything we need for this. So we'll tell the macro to stop, and it should be saved in that location. Okay, in Notepad++, I have the Java macro open that we just created. First thing I want to do is make sure that the line spacing, line ending, is the correct format for whichever supercomputer you're using. In our case, it is a Unix. And so what I'm going to do is, I actually already have a working Java macro that I've used in another for another project, and I'm going to go ahead and borrow some of this code. And so the first thing I want to do is notice that there are only 2 executes, so as public class, extends, whatever, and so we want to make sure that that's the same. And so here, this execute 0 and execute 1, so this execute 2 we don't want. I want to get rid of the execute 2. And then it looks like this execute 1. Again, I don't know exactly the specifics of this code. I just know that it has worked, and it's worked well in the past. So we're going to go ahead and put that code here at the end. So it looks like it has 2 get simulations. We probably don't need that. Okay, it's probably because we saved it out, and that's why it made a new one. So here we have execute 0, execute 1, execute 0 is here, execute 1. And now we want to go ahead and grab this while loop. And this while loop is inside of execute 0, and the final bracket is before the other final bracket. So let's go ahead and grab this while loop and these two variables. We'll put those in there, and then we'll add the see here, where was that again? The end of this is right before the next void. So we'll go ahead and add that there. So now we have, those are correct. And so simulation gets the simulation, automated mesh, it gets the mesh. It says set the base size. We probably don't need to have 2. So we can go ahead and set this base size to I. This I looks like 1.25. Let's adjust that. So what do we say? We want to start at 0.1. And we want it to increment in increments of 0.02. Okay, now we want the initial j, since we're just starting out, we'll put it as 1,000. We could put it as 0, and then it'll add 3,000. We'll do 3,000 for the first time. From my experience in this problem, doing it and setting up, 3,000 will be plenty of iterations for it to converge. So we go down here and find maximum number of steps in the stopping criteria are going to be j. And the next and final thing we want to do is we want to add this interesting piece of code which allows it to save iteratively. And so we'll go along here and we can put this here at the end for both of the save states. So it resolves the path, and so we'll need to change this path as well. And so we can and that's done by just looking at whatever directory you're working in. And so in our case, for the supercomputer that we're using, this is the directory. And so go ahead and change this directory. So we're on the example O2 copy instead of visid. So here, take out the visid. Now we'll put the same in the other side. Okay, so now this should be good. Next thing we're going to do is create a .sh file, and so this will tell the supercomputer to load STAR-CCM, and it'll tell it to access the Java file and load the correct sim file. And so there's a nice JavaScript generator here. So here are some of the parameters we can fill out, and it'll create the code below. So we don't want it to limit to one node because we want to use a lot of nodes. So 64 nodes should be 64 cores should be good. There are about 32 to 64 cores per node, and we don't need any GPUs. 1 gigabyte per processor should be just fine. We want to bump up our wall time significantly more than 1 hour. It's not a test job, it's not a preemptible. If you put it as a test job, it'll instantly run, but it also has the potential of instantly being kicked off. And preemptible means that the job can be stopped for any reason on the supercomputer. And the reason for this is that it'll put you higher up in the queue, so we'll get on the supercomputer faster. We will need licenses, but we'll put that in manually later, and we will definitely want to have it tell us beginning and ending for our email. So update the script. Now we can copy and paste this into our Notepad++. So we want to create a new one, we'll paste it. Now we want to save it specifically as a .sh file. So we want to say all file types, and here we want to get out of this folder and go. Here's where our examples are. So we want to go run.sh. Once it does that, it recognizes the type of code. So a couple things we want to do here is, so you want to have your correct email in there. We've got all of this should be good. So now I have one that I've already created, and we're going to want to put in these the license for STAR-CCM. We only need one license regardless of how many cores we use. So we put the license in there, and then all of this is exactly the same, and we want to put on the load modules. So the module you want is the same module that your STAR-CCM original was created on. So our supercomputer has several different STAR-CCM, 9 point whatever, but you'll need to have the same module so that in case they're not cross-compatible. And then STAR-CCM plus -MPI Intel, MPI flags. So coding number of processors here is slurm in tasks. So you look up here in tasks 64. That tells it that it can parallelize with 64 processors. Machine file is in this directory here. We want to do a batch. Batch script is our JavaScript, and we want to change this to what it was, what we named it as macro. So let's just say that you wanted to not have it called macro, but you wanted to have it called something else. If you want to do that, you have to change it in 3 areas. First, you have to change it in this class. If you don't change it here, it will not work. So let's say example run, ex run, or run x. Okay. So now we want to file, save as. It has to be exactly the same as that. RUNEX. Save. And then we need to come over here in this batch job, run x. So this is the batch, and then this $1 means that in the command line you will put in the name of the sim file. You could also put another $1 over here, if I'm not mistaken, and you could put in the name of your JavaScript. But for our case, this should be good. So we'll go ahead and save that and make sure that everything's the same. It appears to be, so that should be good. Okay, so one of the things that I like to do is to make sure that the JavaScript will run on STAR-CCM before I actually send it to the supercomputer, so that way I can catch some of my mistakes. One of the things that I did already make a mistake on was that I forgot to delete this. In order to get it to run STAR-CCM, I commented these out because the path is different. And then as well, I changed some of these numbers so that it just runs just very, very quickly. So let's say this 0.05. Save it, and let's go in here into STAR-CCM and see if it runs. So it's running, and it looks like it's changing the mesh. Super coarse mesh, but I'll pause it here for you. Okay, so it's about to finish up the mesh here, and let's see if it makes it all the way through. Okay, there, finally completed the mesh, and now it did the 5 iterations that I asked it to, and has continued to do the mesh again. So it is indeed going through the while loop. So we can go ahead and stop it, and let's clear the solution. And then we want to save this, and let's change this back to the values that we want. initialize this as a 3000. Actually, we'll say this is 0, and then we'll, at every iteration, it bumps it up 3000. We'll bump down the mesh size by 0.02 every single time until it is less than 0.05. And then we also want to start this a little bit lower, 0.1, so we'll start it at 0.8. And you can see this is 0.2. 0.3, so that way when it makes it all the way through as 0.2, it doesn't try and do 0. So everything should be good. Let's save this again, and then okay, now we want to put everything on the supercomputer. So I'm going to go ahead and open up Bryce SSH client. I really like this one because it has a GUI interface for transferring files. So I'm going to go ahead and log in, and so I downloaded this just off of the website here. In the documentation, there's batch information, file transfers, and it has a link for the Bryce client. So it opens up two things. It opens up here this GUI that's really nice for transferring files, so you don't have to remember all of the commands for transferring files, and also opens up this the command line. So I'm going to go in. I'm going to go ahead and delete everything that I've done before from other projects, and also in this compute file, kind of clean everything up. And now in the project here, our example, let's see here, which one was the most recent? Example 2.0. So we're going to go ahead and pull him over. And then, while that's working, let's go ahead and uncomment the saving criteria. So we'll save that. So I like, actually, up here, I actually like putting it in saving it in a compute file, which this is the directory for inside the compute file, and that's actually the same directory as I have here. However, I like putting my files in this other area, which I guess I actually didn't do. But so we need our sim, and let's go ahead and rename that. We can exit out of STAR-CCM so that we can let us rename it. And let's just say this is run example. Oops. And put the file type on the end. And we'll go ahead and transfer him. And then we also need the run example and our run.sh file. Run.sh, yeah, that's run example. So run example should be good. So everything's in there now. And so the commands, you can find the commands in the documentation for the supercomputer on the BYU Supercomputer website. But we want to do an sbatch, and then our sh file, run.sh, and then we want to do a run example.sim, and hit enter, and our batch job is now submitted. So it will send me an email here pretty soon telling me when it's started, but I can also take a look through this console by typing in scontrol this control show job, and then I can copy this number right here, and for some reason on my computer when you highlight something it's copied and then you just right click it and it pastes it. So then we hit enter and we look and we say, oh, I guess it's already running, which is great. It's been running for 35 seconds. And so the way we set it up, when it ends or if it fails, then you will get an email saying so, and you can go in and debug, see what's gone wrong. If not, when it's finished, it'll tell you it's finished. And then the way we have it set up is that in this compute folder, every time that it finally makes it through the mesh, it will save, and it'll save out the file. And so as it's running, I really like doing it this way because you can have it running and have it do this iteration through the while loop and pumping out your grid convergence study, and then you can take a look at it as it's going in process and kind of at checkpoints. And so that way, if something goes terribly wrong, you can catch it in the rough before it, you spend 10 hours, waste a day waiting for it. So we'll go ahead and end here. We'll pick up again when we look at the final solutions. So there was one quick problem that I had. As you can see, it said it completed. The problem I had is in the while loop here. I didn't set this as small enough. I thought I did, but I guess that didn't happen. So we'll tell that to save, and then you can just copy over the files that you want here. Just copy it straight over and then say overwrite, and then run in the same controls there. One thing to do, we can see sometimes another thing that I like to do is move this save simulation up to the top. So right after it gets the simulation, then it saves it, and so that way as it first starts, you don't have to wait for the 10 minutes for it to make the mesh. So let's go ahead and put this back in here, overwrite, device, sbatch, our run.sh, and run example.sim. Again, submitted. And let's see, as control, show job. Since it's running, it's started for 20 seconds. There, it started. It started on the mesh. It saved, so it should run through now, and so it's great. Okay, so look back here in the file here in the compute file that I've had it dumping the files into. It looks like the 8 is finished and the 6 is started, and so I've already done this, but you can just drag and drop and copy the file over into the directory that you'd like to, and then that file, that 08, I've already opened up here in STAR-CCM. You can see the residuals have dropped off, and we've got this sort of repeating pattern, this noise, and that seems to be from some numerical issues, which can be seen in this plot in the scalar scene. So this is just the center, the periodic boundary plane, but the problems are most likely from this coarse mesh here at the interface. And so finer mesh, as the mesh becomes finer in the while loop in the Java macro, that should fix those problems. Here's another scalar scene on the top cut plane, just as kind of a how-to. You can make this represent the full, make a complete by not doing that, but by coming in here into the scalar scene 2 and edit, and then here opening this scalar 1 property, we could say it's smooth fill. And we could also look at this in the transform and see the different transform interface 1-1, and that'll make it the complete solution. Looking at the thrust monitor plot, it seems to have leveled off here at about negative 0.19, and that seems that's quite close. The actual values for this propeller at this rotation speed and the advanced speed, the wind tunnel, the incoming, is supposed to be somewhere around 0.15, and so we've got 10-20% error here, but that is most likely due to the fact that in our continua we have our models, we don't have any sort of turbulence, we don't have any sort of compressibility, and if you calculate the velocities and the pressures on the propeller side, it's actually gets quite high, and it is actually incompressible. The Mach number above the propeller, it gets quite high. So now that we have this, it seems to be converging, and so we can continue to get the files from the Supercomputer folder as they come out. You can also parallelize this by submitting multiple jobs, and so the torque monitor plot is also leveled off here. I haven't calculated what the torque should be, but so further work to do to better match, better validate, get this study to validate the actual values for wind tunnel testing would be to change the physics and refine the mesh, and also that boundary layer. And so I hope that this tutorial has been beneficial to you, and that many people will be able to use it for research, for classes, or for just general how-to for personal use.